Good day everyone. So we are now on part 3 of the three-phased review for unit operations, and this is for the course Chemical Engineering Review 4. Now for this review, we will be discussing 3 unit operations: distillation, leaching, and membrane separation. Now for the 3, we're going to start first with the unit operations we call distillation. And in the next slides, you will be seeing the basic principles concerning distillation. Now, when we speak of distillation, it's a process that utilizes vapor and liquid phases at essentially the same temperature and pressure for the coexisting phases and zones. Now, there's a mention about zones here because in our equipment or in our column later on, we will have 2 zones in which all of the components of our phases are the same. Now, our column or our equipment in this case uses random or structured packings, plates, or even trays, just like gas absorption, to bring about the 2 phases into intimate contact. So the 2 phases that are to be contacted here actually are the liquid and the vapor phases. Now, the column or the equipment may be operated continuously or in batch mode depending on a number of factors, one of which is scale, flexibility of operations, and solid content of the feed. Now, take note that all components are present in both phases. And why is this that all components are present in both phases? It's because this time, contrary to the last unit operations that we have discussed, the vapor phase is just created from the original liquid phase, which is the feed. So the vapor was created from the liquid phase feed by the process of vaporization. Now, the feed material, which is to be separated here into fractions, is introduced at 1 or more points along the column shell. In our case, we will only be limiting our discussion to a single feed stream into our column, or that is, we will only have one feed that is introduced into our column. But in reality, in industry, it's not limited only to a single feed column. Now, liquid or the liquid feed runs down the column, or the liquid phase runs down the column, cascading from tray to tray or stage to stage, while the vapor flows up the column, contacting the liquid at each stage or tray. Now, liquid reaching the bottom of the column is partially vaporized. So take note, it's not all vaporized, but only a portion is partially vaporized in a heated reboiler. Now, what's the purpose of this? So that it will provide the boil up, which is sent back up the column. So it is the vaporized part of the liquid that goes down that flows countercurrent to the liquid that goes down. So the remainder of the bottom liquid that was not vaporized is withdrawn as the bottoms product, or simply the bottoms. Now, what about the vapor? The vapor reaching the top of the column is cooled and condensed to liquid in the overhead condenser. So part of this liquid, again, the liquid coming from the condensed vapor, is returned to the column as reflux to provide the liquid overflow. The primary purpose of the reflux, aside from providing the liquid overflow, is to enhance the quality of the final product, which is referred to in the last bullet, the distillate. So the remainder of the overhead stream that was condensed is withdrawn as distillate or overhead product we refer to as the final product. Now, the lighter, low boiling temperature components in distillation tend to concentrate in the vapor phase because that's the primary goal, while the heavier, higher boiling temperature components concentrate in the liquid phase. So the composition of the vapor in equilibrium with the liquid at the boiling point of the liquid should be different from that of the liquid. Now, the vapor phase becomes richer in light components as it passes up the column, and the liquid phase becomes richer in heavy components as it cascades downward. Now, overall separation in distillation can be achieved between the distillate and the bottoms depending on primary on this particular reason. So it could be relative volatilities of the components, the number of contacting trays in each column, and the ratio of the liquid flow rate to the vapor phase flow rate in each section. Now, the column is divided into an upper section, which is often called the rectifying section, and a lower section, which is often referred to as the stripping section. So again, the upper section is the rectifying section and or the enriching section, and the lower section is referred to as the stripping section. This section that was referred to in the first slide are actually also the zones. So take note of the primary factors in which the separation of the distillate D from the bottoms B or W are dependent on. So it's dependent on this: relative volatilities of the components, the number of contacting trays or stages in each section or zones, and the ratio of the liquid phase flow rate to the vapor phase flow rate in each zone or section. Now, in distillation, we have equilibrium diagrams, and these particular equilibrium diagrams gives us the relationship between the mole fraction of a solute in the liquid phase and a mole fraction of that same solute in the gas phase. Now, what you are seeing here is the X and Y equilibrium diagram for the component benzene in a particular liquid. So this is how the benzene distributes itself in that particular liquid. So in the liquid phase, this is its mole fraction, and in the gas phase, this is its mole fraction. Now, alongside this curved relationship between XA and YA, you have this standard written 45-degree operating line. It's written together with the curve. Now, in distillation, we use this particular 45-degree line so as we could properly write or illustrate the position of our operating lines for the enriching and the stripping section, which I will be pointing out to you later in the slides. Now, what about this 45-degree line and this curve? Now, the greater the distance between the equilibrium curve or line and the 45-degree line in here, the greater the composition difference between the vapor and the liquid. The greater the composition difference between the vapor and the liquid, the greater the ease in separation. Meaning, it is easier to separate the component from the liquid, transfer it to the vapor if the composition of the two phases are different, or shall we say have a big difference. Now, we also have this what we call relative volatility. So it's a numerical measure of the degree of separation of the components of a particular mixture, and it's represented oftentimes by alpha. Now, this relative volatility gives you this ratio of the mole fraction of A in the gas phase over the mole fraction of A in the liquid phase. In that denominator, you have the mole fraction of B in the gas phase over the mole fraction of B in the liquid phase. This is for a two-component mixture, because what you see here as 1 minus YA and 1 minus XA represents the mole fraction of the other component in the mixture. So you're actually taking the ratio of the mole fractions of the gas to the liquid phase for both components A in the numerator and in the denominator B. If you don't have the mole fractions of A only or of B only, you can use their pure vapor pressure. So, relative volatility of A with respect to B is the ratio of the vapor pressure of A and B. So, A being in the numerator and B in the denominator. Now, should we interchange the manner of writing the subscripts for relative volatility, it changes everything, because it changes the way we take the ratio of the two, whether it's mole ratios or mole fractions or pure vapor pressures that we are using. If this is alpha sub BA, then this should be pure vapor pressure of B divided by pure vapor pressure of A. Now, how does relative volatility tell us whether separation is possible or not in distillation or in anything or in any separation process for that matter? So, separation is possible whenever alpha has a value greater than 1. Now, alpha varies with concentration, but for binary mixtures obeying Rayleigh's law, the variation is negligible over a large concentration range at constant pressure. There is a variation, but its variation is negligible, meaning it could be neglected. Now, as to the topic of relative volatility in your handbook, please go to section 13-7 and 13-17. So you have to refer to those sections. Now, when we speak of the process of distillations, there are two methods. So one method is when vapor is produced by boiling the liquid mixture in a single stage, recovering and condensing the vapors with no liquid allowed to return to the single stage still or equipment to come in contact with the rising vapors. Method 1 does not have what we call reflux, because in this case all vapors are withdrawn and condensed, so they are all converted into liquid, and that is in method 1. What about method 2? Exactly the same as above as method 1 in the manner in which the vapor is produced from the boiling liquid mixture, which is our feed. The only difference is that part of the condensate is returned back into the still or into our distilling column in the form of reflux. And the main purpose was already discussed in the previous slide, and that is to improve or enhance the quality of the final product withdrawn. Now, under method 2, we have fractional distillation or distillation with reflux or rectification. Actually, any of this refers to the same thing. Distillation with reflux is also known as rectification or fractional distillation. Now, let's go to each methods under type 1 or each types under methods, each method. So, we have for method 1 wherein no reflux is returned into the column, equilibrium or flash distillation. So, in the case of this type of distillation, a liquid mixture is partially vaporized. The vapor is allowed to come to equilibrium with the liquid, the vapor that was vaporized. Then vapor and liquid phases are separated, and this particular process could be done continuous or by batch. Now, under method 1, we also have batch or differential distillation. So, liquid here is slowly boiled and the vapors are withdrawn rapidly as they form in the condenser, resulting to a vapor reaches in the more volatile component A, and this is referred to as the first portion. As vaporization proceeds, vaporized product becomes leaner in A, meaning the value or the composition or concentration of A in the vapor that is withdrawn becomes less and less in the case of differential or batch distillation. So the difference, if we're going to compare these two for now, this one is slowly boiling the withdraw and then withdraw rapidly. This one, you are only vaporizing the liquid partially. The vapor that was allowed to come to equilibrium with the liquid is then being separated. Now, we go to steam distillation. This is the common one, and this is the one that is performed in the laboratory in lab scale operations. Now, steam here is used to separate components of a high boiling liquid solution, which lowers the boiling temperature of the high boiling component. The vapors are condensed and the two immiscible liquid phases separated. So, the purpose here is to separate components of a high boiling liquid solution, which of course lowers the boiling temperature of the high boiling component using steam. Now, this is a simple diagram for equilibrium or flash distillation. So, a description was written here to add to what was discussed in the previous slide. So, in flash distillation, we have a portion of the mixture being vaporized, and then the vapor and liquid phases separated. Now, there is always a process of preheating the feed here and throttling it before it's introduced into the separator. We call this the separator that separates the equilibrated vapor and liquid phases. So the feed is preheated in some heating source, oftentimes a heat exchanger, or if not, a furnace. Then it undergoes a process of pressure reduction in using a throttling valve, or it undergoes throttling, and then it is introduced into the separator, which now separates rather the equilibrated vapor and liquid phases. Now, this is a detailed explanation of flash distillation. So, it's the simplest method of separation employing the principle of distillation, and that is capitalizing on the difference in the volatilities of the components present in a mixture. Now, here, a feed stream is flushed into a chamber or flush drum, and the liquid and vapor are allowed to separate under equilibrium. It is flushed by throttling the feed stream through a nozzle or a valve into the chamber, which reduces the pressure. The more volatile component will be concentrated in the vapor stream, and the less volatile in the liquid stream. The system is very close to a single equilibrium stage. And separation here is usually not very high for a single equilibrium stage. So meaning your recovery here is expected not to be good, not to be high. Now, if you're going to have calculations concerning flash distillation, there's a need for us to have an equilibrium equation or an equilibrium relationship, let's say, between X and Y. And there's a need for us to do mass balance or material balance. And aside from that, we need also to perform energy balance. If any of these equations are not possible in terms of the provided information, most of the problem in flash distillation require trial and error solution, if not the aid of a software, so as to accomplish the trial and error procedure in a much lesser given amount of time. Now, let's say for our binary system, so we have only two components in our system, and let's say we will represent the feed as F, the vapor as V, and the liquid as L. And let's say we will represent the composition of our feed as Z in terms of solute A, and that of the vapor is Y, also in terms of component A, our solute, and X in terms of component A in our bottoms or in our liquor. This one is the vapor and this one is the liquid. Now, the 1 minus Z, the 1 minus Y, and the 1 minus X in this representation represents the composition of the other component, because most of the time you're only concerned with the solute. So this 1 minus Z is that of the other components present in the mixture, because we already represented the component that we're interested in by A, or let's say by Z sub A specifically. Same principle applies here for the vapor and the liquid phases. Now, assuming that we choose a basis of the feed flow rate and we have 5 unknowns, the outlet flows in this case, which are V, L, and the compositions X, Y, and Z are these unknowns. So you can set up an overall material balance. In this case, that would be F is equal to V plus L. Then you can do a component balance on the solute. That would be F times Z being equal to V times Y plus L times X. Then you can also use K values whenever possible, or if it's simply the equilibrium relationship Y equal to MX, then this K here, the distribution coefficient, can be an M. And this should be given by the problem. Now, we have so far this mass balance equations and this equilibrium relationship. We still need the third equation, which is the energy balance. And what we do, very simple, we add up all the energies of all the components present initially before the process commenced and after the process commenced. So in this case, it's simply telling you that This is the energy content of component A in the feed because it has Z. And this is the energy content in terms of enthalpy. By the way, all are enthalpies of component B. Why I say component B? Because it's already 1 minus Z. So meaning this is the enthalpy content of component B in the feed. So you have enthalpies of component A and B in the feed is equated to enthalpy content of the vapors also having A and B and the liquid also having A and B. So this is how we do energy balance in flash distillation. So all three equations, now considering this component balance as a separate equation, now we have all four equations to utilize. That way we will determine the unknowns for a given problem. Okay, or we can determine the required information for a given problem. Now, we go to the second type under method 1 still, and this is referred to as differential distillation. So a detailed description of what was discussed a while ago is written also in this slide. So it is a batch and a single stage distillation process that starts with the still pot, initially full, heated at constant rate. In this process, the vapor formed on boiling the liquid is removed at once from the system. So this is a case of slow boiling because you have a heating mantle or a liquid that boils up to heat up the boiling inside this the liquid inside this flask. So since the vapor here is richer in the more volatile component, that is the vapor that is being produced out of boiling the liquid here inside the flask, it follows that the liquid remaining becomes steadily weaker. This is weaker in this component, meaning A here, for example, if A is more volatile, becomes leaner and leaner in this portion, with the result that the component of the product progressively become, or rather with the result that the composition of the product progressively becomes weaker in the more volatile component as the process proceeds. So over time, we expect that our product here being collected will become leaner in the more volatile component. The special distinction of differential distillation is that the vapor formed over a short period is already in equilibrium with the liquid. It does not need the liquid and the vapor to be equilibrated first in the case of the flash distillation. That needs the separation. In here, the vapor that is already withdrawn here is already equilibrated with the liquid. The vapor form is not in equilibrium, however, with the residual liquid, the liquid that remains in here. Then at the end of the process, the liquid that remains in the flask in this illustration is concentrated in the less volatile component. So meaning the much heavier boiling components of your mixture over time is left in this particular chamber. And it is referred to as the bottoms product. And they are more concentrated in terms of the less volatile component. The problem with differential distillation class is most of the problems are solved using graphical integration. So this is just bad for your information and for you to be able to distinguish it specifically with the simple flash distillation. The steam distillation is the one that you have done in the laboratory. Steam distillation is a separation process which consists in distilling water together with other volatile and non-volatile components, and the steam from the boiling water carries the vapor of the volatiles to a condenser where both are cooled and returned to the liquid or solid state, while the non-volatile residues remain behind in the boiling container. Now, under type 2, you can refer to section 13-5 of your handbook for this. We have extractive distillation and azeotropic distillation. So, under extractive distillation, we are employing here, or this is employed rather, when the volatile difference the volatility difference between the two components to be separated is so small that a very large number of stages when already designing the column will be needed. So in this case, in extractive distillation, a mass separating agent is selected that increases this difference, because the lesser the volatility difference between the components of your mixture, the more difficult it is to separate them. So this mass separating agent increases that difference, so that in actual design, our column will have a reduced number of stage also. Now, another under method 2, wherein we have the presence of the reflux liquid, is the essiotropic distillation. And it's an alternative to extractive distillation, the one that was mentioned on top. Now, our main purpose here when we discuss distillation is in the process wherein we have the presence of the reflux liquid. And for that particular distillation, we'll be using what we call as a fractionating tower or a fractionating column. So in this illustration scanned or snipped from your book, I think this is taken from Jan Kuplis, you have the feed, a single feed here being introduced. This feed is liquid, so it goes down, while the vapor coming from the feed that was vaporized goes up, flowing countercurrent to the liquid that goes down. The vapor that goes up is condensed here in the condenser. Some of the condensed liquid is returned as reflux. So this is the main thing that makes this particular design interesting, because it enhances the quality of the final product. And this is the other condensed vapor that goes up, which is already withdrawn as distillate. Now, the liquid that goes down rather, are not all boiled up. So some only were boiled up and some are withdrawn here as the bottom's liquid. So liquid here returns and is withdrawn as the bottom's liquid. If you notice, the liquid that goes down is the one also that is being heated here in the reboiler. The reboiler's purpose is for this particular liquid, a portion of this particular liquid, to be converted into vapor, so that we will have a phase, a gas phase that will flow countercurrent to the liquid that goes down. So the same liquid is being heated using steam to produce the boiled up vapor, flowing countercurrent to the liquid that goes down. You can read this in section 13-15 of your handbook. Now, this is not oftenly used, the Ponchon-Savarit method, because a problem normally using Ponchon-Savarit method solved manually will entail a lot of time to finish. So what they do in the case of Ponchon-Savarit, if there's really a need to use enthalpy balance or energy balance together with the material balances in distillation problems, they use softwares. But nonetheless, for your information, the Ponchon-Savarit method uses the enthalpy composition diagram, aside from the equilibrium diagram, wherein we can draw together with the 45-degree line and the equilibrium curve our operating lines. And in the case of distillation, we have 3 operating lines for that. But for this one, this is not graphical because it's all analytical. However, the process really is long because it has some portions, or it has a portion rather, that you need to do trial and error. And you cannot proceed unless you are already satisfied with your values. And that is the value that you assumed already tied with the value that you use to validate it as you proceed in your calculations. So approach here uses the energy balance in addition to the mole balance and phase equilibrium relationships. So constant molal overflow, again, in this case, is not assumed. In MCCABE-THIELE method, we use this assumption of constant molal overflow. We are not to do, or we're not allowed to use that assumption when we use Ponchon-Savarit. Anyway, it's in section 13-16-17 of your handbook, just in case you want to complement what is being discussed here. Now, the MCCABE-THIELE method is based upon representation of the material balance equations as operating lines that I have mentioned a while ago. So, the operating lines are made straight. So, the reason why they are called line by the assumption of constant molal overflow, which eliminates the need for an energy balance. So, we assume it's constant molal overflow so that we will not have to resort using the energy balance. Now, the liquid phase flow rate here, so as to explain, by the way, what is this constant molal overflow, it's being explained in this bullet. So, the liquid phase flow rate is assumed to be constant from tray to tray in each section of the column between addition, between the feed, and the withdrawal, that is the product, which makes the vapor rate to be constant as well. So, we assume, it's a crude assumption actually, just to simplify our computation. That way we will not have to resort to energy balance. A crude assumption, I say, because this one assumes that even though some components of the liquid have been already transferred to the gas in the process of distillation, we still assume that the transfer is, shall I say, very gradual, that the decrease in the value of the liquid phase as it goes down each tray or each stage is very negligible. Like, it's just like saying that L1, let's say L1 is the liquid phase that enters stage 0. L1 that leaves that particular stage is still equal to it. L1 is the stage that leaves, is the liquid phase that leaves stage 1. So we say that it's the same or more or less equal to the liquid that entered the same stage, which is LO. That is what is meant by assuming that liquids that goes down are assumed to be the same. They are not affected. But in reality, class, in terms of value, they should decrease. But the decrease is assumed very minimal because a portion of it has already transferred to the vapor phase. The same way, we don't expect, or we don't calculate that the vapor that goes up will not increase in its value in terms of the number of moles that it has, even though a portion of the liquid that it contacted with has already transferred a component to it. So there's no corresponding increase, or shall I say, there's no notable increase in the value of that vapor. So in constant molal overflow, that is being considered negligible. If we don't do that, then there's a need for energy balance. And that would be now method Ponchon-Savarit. So you can read this on section 13-18 of your handbook. If we look into the liquid flows on each tray, this is a cut portion of the schematic for a distilling column. You could see here that the liquid phase, let's say entering stage N, is Ln minus 1, and this one is Ln, the liquid that goes down. In constant molal overflow, we assume that these two are equal. Same thing with this vapor, these two are equal. When we do material balance, it's the same with other unit operation processes, especially the ones that are multi-stage, or the ones that can be done multi-stage, that we add up the streams that enters a particular stage. In this case, that would be V sub n plus 1 and Ln minus 1. Here, V sub n plus 1 and Ln minus 1. And we add up to that the vapor and the liquid phases that leave. So this is V1 and this is L1. Okay, we add the two. They should be the same. Our component balance is patterned after the material balance. We only affix the mole fractions, or the concentrations of the vapor and the liquid phases. Vapor composition is Y. Liquid phase composition is X. Now, our column, when drawn simply, will be something like this. You have the F, the XF for the feed. We have the D for the distillate, and X sub D. And we have W. In some books, this is capital B, X sub W for the bottoms liquid. Overall material balance would be F being equal to D plus W. And again, the component balance is patterned from the overall material balance. So we affix the appropriate representation of the mole fractions. Notice that all are X because everything now is in liquid. Though we have vapor going up here, it's being condensed and converted into liquid. So everything there now is in liquid form. I'm referring to the concentrations that you are summing up. Now, there was a mention in the beginning of the topic that your distilling column or your still has two sections or zones. The upper section is the enriching section. Of course, the lower section is referred to as the stripping zone. So the enriching section or the rectifying section, when drawn on the 45-degree line and on the equilibrium curve diagram, which is the equilibrium diagram, will be situated here. So I will not anymore explain how the graphical approach should be done because this was explained to you already. So our main focus now is on the analytical process of determining the stages. But nonetheless, this is your operating line for the enriching section. And the enriching section is, of course, the section on top of the feed line. Now, if we do a total material balance for the enriching section, this would be our material balance and this would be our component balance. You can refer to your handbook for its equivalent there. We have an operating line equation, and since it's a line for the enriching section, that line is equal to or can be represented to as y being equal to, and I'd like here to focus on the occurrence of the R, the reflux ratio together with the concentration X sub D. So it's a line equation because the R over R plus 1 is the slope of the line, and this X sub D over R plus 1 is the y-intercept of that line. So this is a line of the form y equal to mx plus b. Now the R here is the external reflux ratio, and it is actually equal to L sub n over D. And we also have what we call as the internal reflux ratio, which is L sub n over V sub n plus 1. So take note, the R here is the external reflux ratio, the L sub n divided by D. And this particular equation for the enriching section or rectifying section operating line is the one that you see in section 13-19 of your handbook. Now, the stripping section is of course the bottom part of your column. It constitutes the reboiler, whereas the enriching section or the rectifying section is the upper part of your column, which constitutes the condenser. So this is your reboiler, and now the operating line for the stripping section is written. Okay? And you know already how this particular operating line is drawn. Actually, this is the last of the three operating lines that is written in this equilibrium diagram. Because after the rectifying section or enriching section operating line, what we draw next is the feed line. Then, wherever the feed line and the enriching section operating line intersects, that's where we connect the end of this stripping section operating line. So, the intersection of the two determines the orientation of this third operating line, which is your stripping section operating line. Again, refer to this section in your handbook for a detailed explanation on the sections of your distilling column. Just like your enriching section, we also have a total material balance for this section, and its component balance is of course patterned also from its total material balance. And the operating line for the stripping section is given by this. Now, I have mentioned that when we do graphical approach in determining the number of stages for distillation, the stripping section operating line, this one, the stripping section operating line is the last line to be drawn. Why? Because after the enriching section operating line or the rectifying section operating line, we draw first the Q line or the feed line. It gives us a graphical representation of the condition of the feed. And for us to be able to quantify correctly the condition of the feed, we need to know the Q. And what is this Q? I gave you here two definitions of the Q from two different authors. The one you see on top is the definition of John Couples. The one you see here is that of McCabe. So Q is defined as the heat to vaporize 1 mole of feed at entering conditions divided by the molar latent heat of vaporization of the feed. It's the heat to vaporize 1 mole of feed at entering conditions divided by the molar latent heat of vaporization of the feed. If McCabe defines it, it is the number of moles of saturated liquid produced on the feed plate by each mole of feed added to the tower. Number of moles of saturated liquid produced on the feed plate by each mole of feed added to the tower. And speaking of the feed location, based on this feed condition, your feed actually is in the stripping section. And that was only mentioned in McCabe. So it's mentioned in McCabe that your feed is in the stripping section. Now you have here for specific values of Q for special conditions of the feed. If your feed is vapor, that is saturated vapor, your Q value is 0. If it's saturated liquid, its value is 1. And if it's subcooled liquid, its value is greater than 1. If it's superheated vapor, its value is less than 0. So this is your checking. If you have a subcooled liquid feed, the Q value that you will be getting should be greater than 1. If you have a superheated vapor, which is less likely to happen, but it may be given in a problem, your Q is less than 0. If your feed is part liquid and part vapor, Q is the fraction of the feed that is liquid. Take note. If you have a mixture of liquid and vapor in your feed, Q is the fraction of the feed that is liquid. So we expect it being a fraction, its value should be greater than 0 but less than 1. So this is found on section 13-19 of your handbook. Now, as two equations that would help us determine the Q, the one you see here on the left is the equation provided by John Couples. This one is from John Couples. Well, I have here an equation from McCabe. So, McCabe also gives a summary of the different equations for the Q for specific conditions. So, please check on McCabe. What I have written here is specifically for the cold liquid and the superheated vapor. That is, if it's not saturated liquid and if it's not saturated vapor, then you should have equations to use, and that's only provided by McCabe. So please go to McCabe and check for those equations. Now, if you have been provided by the problem, or if there's a means for you to determine the Q value given the enthalpy of the vapor, the feed, and the liquid, you can use this equation. So, enthalpy of the feed at the dew point is H sub V. Enthalpy of the feed at the boiling point is H sub L. And enthalpy of the feed at its entrance condition is H sub F. Take note, enthalpy of the feed. So, all is the enthalpy of the feed, this time at its dew point, meaning it's about to be converted to saturated vapor. Enthalpy of the feed at the boiling point is H sub L, and this one is enthalpy of the feed at its entrance condition is H sub S. So this one will work if you have the enthalpies. Now let's proceed. So your Q line equation, since it's a line, it's also that of an equation of a line. So the slope of that line is dependent on the Q. Its y-intercept is dependent on the feed condition and the Q as well, because you have here the mole fraction of the feed. Now, this is now the graphical representation of how we, shall we say, properly place in or draw our operating lines, specifically based on the feed condition. So this is your enriching section operating line. And let's say, for example, you have a feed which is a mixture of liquid and vapor. So your Q will be having a value which is somewhere between 0 and 1. So this is your feed line. So since you already have this intersection for the feed line and the enriching section operating line, what you do, you connect the intersection here to X sub W to draw properly your stripping section operating line. So of the three lines, the stripping section is the last one drawn. For other values for Q, this one is for subcooled liquid, this one is for saturated liquid, this one is for saturated vapor. And we don't have here superheated vapor. So we only have subcooled liquid orientation here. But nonetheless, these are the different orientations of your Q line or your feed line based on the value of the Q. Again, refer to this section 2 for more elaborate explanation. Now, the feed plate location I have partly mentioned a while ago. It's in the stripping section. But if you will be asked by the problem on the specific plate where feed should be introduced, if it's to be determined using graphical approach, it is the plate where the change of location of one step transferring from the enriching section to the stripping section right away occurred. In this case, since this is where the three operating lines met or intersected, then the transfer of the stages here when you do it stepwise will be from this particular line going down straight to the stripping section operating line. We don't do it as in A, wherein we have based the location of the feed plate on the length of the line that we have drawn for the enriching section. In this case, as you could see, since the enriching section operating line was extended, the manner in which these steps were drawn was based on the length of this extended line, which is wrong. By the way, it should have been from this point going here down straight to the stripping section operating line. It should not be based on the extended line for the enriching section, but rather it should go down, transfer right away at the very first opportunity to the stripping section operating line. So this is how we determine the feed plate location graphically. The MCCABE-THIELE diagrams allows us to determine the number of stages that will recover or accomplish the recovery for distillation. So we start stepping off our line on the upper portion of the enriching section operating line, which is determined by the composition of the distillate. Then we go down until we go beyond or right on the composition of the bottom's liquid, which is the starting point for the stripping section operating line. Of course, this will be done erroneously if we have extended the location of the feed tray based on the extension that you should have made here for the enriching section operating line. But since this is review, you will not have to do this because you will have to do the analytical approach. If it's the total reflux corresponding to the minimum number of stages, there's no need for you to draw the operating lines. Because in the case of total reflux, your operating lines for enriching section and stripping section are all coinciding on the 45-degree line. They are all on this 45-degree line here. So then, we just step off our number of stages graphically by starting from X sub D and probably going beyond or ending right on X sub W. And this is the minimum number of stages at a condition of total reflux. In the case of total reflux class, all the reflux liquid are returned back to the still, meaning there's no distillate that is withdrawn in the case of total reflux. So refer to this section in your handbook for the additional readings on this topic. Now, on conditions of total reflux, so all product distillates and bottoms are reduced to zero. So I have mentioned already that there's no distillate because all the condensed vapor is returned or refluxed back into the column. It's the same thing with the bottoms. Bottoms liquid here are all reduced to zero. That is, all liquid in the bottoms are reboiled, everything. So your liquid that goes down are not partially vaporized. They are all vaporized and returned back into the column, flowing going up rather, in the form of vapor, and return to the tower as vapor. All overhead condensed vapor are returned to the tower as reflux, meaning total reflux. So this requires infinite sizes of condenser, reboiler, and tower diameter. What does this mean with requiring infinite sizes? Meaning, in terms of design class, we cannot limit how big our condenser, our reboiler, and our tower diameter in this case. Why? Because we have, in this case, the minimum number of stages. Our main goal is to minimize the number of stages that will accomplish the desired separation. So infinite sizes, meaning we should not limit the design of the condenser, reboiler, and of course our column itself. Now this gives the minimum number of trays to be used to obtain the given separation. Now, as for minimum number of trays, there's this equation by Finsky that uses the relative volatilities of the overhead vapor and the bottoms liquid. And what we do, we take the geometric mean of these relative volatilities. How do you determine the relative volatilities? You go back to the definition of relative volatilities. The ratio of the pure vapor pressure of the component to the other component that we are not concerned of. So let's say the relative volatility of benzene in the bottoms liquid is equal to the pure vapor pressure of benzene based on the temperature of the bottom liquid divided by the pure vapor pressure of toluene if it's with toluene in the bottoms liquid as well. So that's how you get the relative volatility. So if it's the overhead vapor that you want to get the relative volatility, the same formula or principle you should apply. Get the geometric mean and apply it here, and you will get the minimum number of stages or plates that will be required for the desired separation. Now, if we have minimum number, or rather if we have total reflux and we have minimum number of stages resulting from total reflux, then what is minimum reflux? If you have total reflux, what's minimum reflux? And it's represented by R sub m. It is actually the reflux ratio that will require an infinite number of trays for the given desired separation. This time, if total reflux results in the minimum number of trays, minimum reflux results theoretically to an infinite number of trays, meaning it's not possible. You cannot count the number of trays that will facilitate or that will ensure that we have the same degree of recovery. So that is the case of minimum reflux. So in this condition, we have minimum vapor flow into the tower and minimum condenser and reboiler sizes. So meaning your condenser is the smallest possible condenser that could be designed. The same thing with your reboiler. And your tower, of course, can have its smallest design possible in terms of diameter. Why? Because of the minimum vapor flow. In this case, not all the liquid that goes down is boiled up or converted into vapor. It's the exact opposite of the total reflux condition. Now, the operating lines, referring to the enriching and stripping, moves farther from the 45-degree line and closer to the equilibrium line, which makes the number of steps required infinite. And this is minimum reflux. If you're doing it graphically, class, you cannot count the number of stages because they will somehow merge here and there's no way to count, or there's no way to draw in the first place the step that would be coming from the enriching section that would be transferring to the stripping section. Why? Because your operating lines here, referring to the enriching section operating line and the stripping section operating line, all dwelled away as far as possible from the 45-degree line and touch the curve in here. Now, where these two met on the curve, which of course results to an infinite number of stages, is this point we call the pinch point. From in the pinch point, there will now be it's a point wherein, shall we say, there won't be any transfer already or recovery already of the component that needs to be separated from the feed. Okay, read on this on section, read more on this in section 13, that's 24 of your handbook. Now, how do we determine the minimum reflux? The minimum reflux is determined using the pinch point coordinates. The pinch point coordinates x prime and y prime, and you will be able to get the r sub m. So your x prime and your y prime are the coordinates of the points of intersection which lies on the equilibrium curve of the two enriching and stripping section operating line. How do we determine the minimum reflux? That's already given in the equation in the previous slide. It could also be something like this. The pinch point is not here because the three lines already merged here. It's referring to the enriching section, the stripping section, and the feed line. They met here or intersect here, but it's nowhere situated on the curve. Your pinch point now is on the tangential portion of the enriching section operating line here. Why? Because there won't be any transfer anymore. If you do stepwise pattern here, it cannot transfer on this section anymore because of this pinch point here. So this is also corresponding to a condition of minimum reflux. Infinite number of trays because your enriching section operating line has been tangential on a portion of your equilibrium curve. Now, what is the operating reflux ratio? Operating reflux ratio. So, this is based on, or rather, sorry class, the optimum reflux ratio. This is based on the economic balance of the fixed cost of the tower and the operating cost. So, its value is dependent on the minimum value. And it's between minimum reflux and total reflux. It's dependent on the minimum value because it could be as small as this or as big as this. So what we do, we add 20% of the computed minimum reflux, or either we maximize it to 50% of the computed minimum reflux. That way, we'll have the optimum reflux ratio or the optimum operating reflux. Now, in most problems, the optimum operating reflux is 50% more of the minimum reflux ratio. Now, you have here the enriching section operating line for minimum reflux ratio. And you have here your feed line. This is your feed line. And this is your steps for total reflux. Notice that the steps for total reflux are not dependent on, look, it's not dependent on the construction of any operating line. It's just dependent on these 2 points, the x sub d and the x sub w. Now, as for the enriching operating line for minimum reflux, this is what you're going to do so that you'll find the value of the x prime and the y prime that you will substitute in this equation. Let me go back so that you can have the minimum reflux ratio. In the first place, if the process is purely analytical, you should not take this from the diagram. You should be able to determine this analytically. So the procedure that is shown here on the slide where it came from tells you that. So what you do, you solve the equation for the Q line and the Q line and the enriching section operating lines simultaneously, just like what you do in algebra. Two equations with two unknowns will give you the value of the x and the y, or specifically the x prime and the y prime. Now, since you know that already, you can go back to the equation I've shown you regarding minimum reflux, and you can solve now the value of the minimum reflux. You don't need to draw the lines anymore. Just get the intersection of the enriching section operating line and the feed line. That should be your x prime and y prime, or that should give you your x prime and your y prime, so that you can find the R sub m. Now, as to determining the number of stages without having to draw it or doing graphical approach, you have a similar figure to this in your handbook. I only got the one that is available in the textbook for illustration purposes. Now, what you have here on the horizontal axis is n sub m and n. Meaning, if you have the value of this already, together with the minimum number of stages, the n sub m, you'll be able to get the theoretical number of stages. Now, prior to that, then there's a need for you to determine the minimum number of stages using Finsky's formula. And that is using the relative volatilities of the bottom's liquid and the distillate. Now, then, you still need to know the R, so that you can solve for R over R plus 1, which now will be used as your Y. And then the R sub m, which I discussed to you a while ago, will be these curves that you have. If your R sub m is nowhere to be like exact on the curves that you have here, you can approximate the location of that particular curve here. So having the Y and having the Rm over Rm plus 1 value, you'll be able to get the X, which will of course give you the N after you have substituted the minimum number of stages. So it's not graphical approach, it's simply dependent on this correlation by, in this case, Erbar and Maddox. So that's how you determine the number of stages. As to location of the feed plate, if you're not doing it graphically, you have this ratio given by Jen Kuplis, the ratio of N in the enriching section to that of the N in the stripping section. You may use the common log here, log, or the natural log, which is the ln. Now, in here, you need the x of the x of the LF, HF, and the x of the LW, HW. So this is for the bottom's liquid. This is for the distillate. And this is for the feed. The H here refers to the high boiling component. The L here refers to the low boiling component. The same thing in here. They are all X. They are all mole fractions in the liquid. This is for the feed. This is for the bottoms. This is for the distillate. The low boiling point component, or the solute that we want to recover, and the high boiling component, of course, the solute that remains in the bottom's liquid. Using this formula gives you the ratio of Ne to Ns. Okay? Now, how do you determine the number or the feed plate location if you already got this? Let's say you already have a value of 10 here. How would you know the feed plate location? If you have the number of stages, the total number of stages, your N over Ns equal to 10 should give you like the ratio of Ne to Ns. And if you are to construct shall we say, an algebraic equation from that ratio, we can say that Ne, based on my sample, is equal to 10 Ns. If the ratio of these two, for example, is 10, that's just an example, then Ne is equal to 10 Ns. In your total number of stages, let's say I be 50, then that should be Ne plus Ns equal to 50. But we know that Ne is already 10 Ns. So you substitute it back on the equation that you have, and you will get the number of stages on the enriching section. Once you have the number of stages for the enriching section, you add 1 to that. That would be the location of the feed plate, because your feed plate is actually on the stripping section. So again, I will repeat. If you already got the value of this, which is 10, that gives you a relationship that Ne is equal to 10 Ns. And if your total number of stages is 50, then it should be Ne plus Ns equal to 50. But Ne is 10 Ns, so it should be 10 Ns plus Ns is equal to 50. So 11 Ns is equal to 50. So Ns is equal to 50 over 11. That should give you the number of stages for the stripping section. Knowing the number of stages in the stripping section, you subtract that from the total. That should give you the number of stages for the enriching section. The number of stages in the enriching section plus 1 gives you the location of the feed plate. Okay, that's how we do it analytically in terms of finding the feed plate location. Read on Janku please as to how this particular equation can be used if you still need to be clarified on some issues as to its use. Now, there are these what we call special cases of rectification, and one of these special cases is stripping column distillation. It's just like your column simply functioning as a stripping column. It doesn't have any enriching section. So in here, feed is usually saturated liquid. So the other scenarios for the feed is already out of the picture here, because your feed is usually in this case saturated liquid at its boiling point, and it's introduced at the stripping column, meaning at the top portion of the stripping section of your column without the enriching section. Now, overhead product VD here is the vapor rising from the top plate which goes to the condenser with no reflux. It's just like you cut the upper portion of the column, then the vapor that goes up in that portion is directly being converted into liquid using a condenser, and there's no reflux. The W here, which is the bottom's product, is rich, of course, in the non-volatile component. The column operates as a stripping tower with the vapor removing the more volatile component from the liquid as it flows down. The liquid that goes down, that is introduced on top of the stripping section, is being, let's say, stripped off. Just like the term stripping, it's being stripped off the component by the vapor that goes up. So the volatile component is being carried by the vapor that goes up the stripping column distillation. So read on this section of your handbook for more info on this. Now, and this is the case of the stripping section distillation, or simply a stripping column distillation. Your feed here is introduced on the top of the section. There's no enriching section anymore. And in this case, when you draw it graphically, you have a Q line that is vertical because it's saturated liquid. And you're using here the YD, or the mole fraction of the vapor that goes up the column, carrying with it the volatile component, or the most volatile component. This YD anyhow is just the same as XD, because whatever is the mole fraction in the vapor here is the same mole fraction in the condensed liquid equivalent. So this is how you accomplish it using graphical approach. Now, if the feed in this case is below the boiling point, that is, it's not saturated, the Q line to be used is Q greater than 1. And in this case, the LM is equal to QF. But most of the time, in the case of stripping column distillation, the feed is really saturated liquid. If we have stripping column distillation, we also have enriching column distillation. The same principle applies, only that this time your column is only the upper portion. It does not have the stripping section. It only has the enriching section. Distillate is more rich on the volatile component in this case. The bottom's product is comparable to the feed in terms of composition, but may at times be slightly leaner in the volatile component. So meaning the composition of the feed based on the most volatile component at times is less than, or rather of the bottom's liquid is sometimes less than that of the feed. If feed is saturated vapor in the case of enriching column distillation, your V sub N is equal to F, and that is the vapor that leaves the end tray or stage. Enriching line and Q line equation holds, and the way it is drawn is the same in principle as if you have the complete distilling column, but this time you only take away or eliminate the lower portion, which is the stripping section. Read on section 13-5 of your handbook for further explanation on this. Now, feed here enters the bottom of the tower as vapor. So, opposite that of the stripping section or stripping column distillation. So, this is your enriching section distillation. Now, we have also what we call rectification with direct steam injection. So, in the case of our distilling column, we're only using steam in the reboiler. We don't use the steam in the column itself. The purpose of the steam in the reboiler is to convert a portion of our liquid that goes down into vapor or to provide the boil up. Now, in the case of this direct steam injection, steam is really introduced into the column, not using the reboiler anymore. So, you see, reboiler exchanger is not needed anymore. So, steam is injected as small bubbles into the liquid in the tower bottom. And this requires an extra fraction of stage since you're stepping when you do the graphical approach or the way you draw your, shall I say, stripping section operating line with the steps in your number of stages is going beyond or below the y equal to x line. That would be shown to you in a little while. This rectification with direct steam injection has the advantage of simpler construction of the heater because, again, there's no need of a reboiler exchanger. There's no need of a reboiler because the steam is directly introduced into the column. Now, in the case of rectification or distillation with direct steam injection, if you draw your enriching section operating line, it's the same thing. Your Q line or your feed line is the same thing. However, your stripping section operating line is not starting here in the 45-degree line, but it goes beyond the y equal to x line as explained in the problem. So it's right on the x-axis. So then it will require an extra fraction of stage. That's what it meant when it requires an extra fraction of stage, because you have to connect this particular step here in here until here, not just in here. So that's the explanation of what's happening on your rectification with direct steam injection. Though it will require an extra fraction of stage, only a fraction, it will not anymore need the reboiler. So the enriching section operating line is the same as in direct steam, so the same, but the stripping section operating line in this case will have a different equation, and its equation would be something like this. Now, that is in the case of using direct steam or when steam is directly injected into the column, not being used in the reboiler. Now, what about rectification with side stream? Though this is not covered, just for your information. So, there are rectification processes wherein there is a side stream. Now, this arises when intermediate product or side streams are to be removed from sections of the tower between the distillate and the bottoms. Meaning, the removal of the product in the case of actual industry application is not always on the top or after the vapor has been fully condensed by the condenser. But the reason why we have actually the term fractionating column, it's because we withdraw specific components or product as fractions from each stages of our column. So, depending on what particular product we are interested in. So, it's not only one particular product that we are withdrawing from our distilling column as the actual scenario in some industries, especially in the case of petroleum refining, but several products depending on where they are to be withdrawn or in what particular section they are to be withdrawn in our column. A specific section withdrawal will give a different product composition because at each section, the components are not the same. Because as we understand, in distillation, we volatilize the most volatile. So meaning the first one that is vaporized is the most volatile. The one that is left at the bottom or at the lower portions are the less volatile. So depending on what you are trying to recover in a particular fractionating process. So if you want to recover a particular side product or product from a particular section because that's what you are interested in, then that's possible in the case of distillation. It's not always a case wherein you only have one product that is to be removed from the condenser wherein all the vapors have been condensed already. Side stream may be liquid or vapor, which can be removed either above the feed entrance or below depending on the composition desired. So I have already mentioned that. Depending on the composition that you so desired. So you can read on this in section 13-18 of your handbook. And this is the case of a distilling column drawn simply wherein we have a stream O that is withdrawn in this section here. But it's not already our coverage for this particular topic, but just for your information. And in the actual industry application, there are fractionating columns which has several side streams depending on the composition of the product that is to be withdrawn. Now, in the case of rectification with side stream, our overall material balance will change because if you could see here, let me go back. You have this O and D and W, and you only have one feed in here. So your V sub S plus 1, if you're going to do material balance in this section, would be your D and your O. Now in here, you could see that your V sub S plus 1 is equal to LS plus O plus D. Now, let us see where is that LSO plus D. So, your VS plus 1, the stream that entered in this section where the material balance was done, is equal to LS, the liquid that goes down here, the O here, and the D. So, it depends on what particular section you want to do material balance actually when we are considering distillation with side stream. Then, you can also have material balance on the most volatile component based on this particular material balance that was done on the box. Your operating line would be an operating line which has LS over V sub S plus 1 as the slope. So, these are the values actually of the liquid and the vapor phases that leaves the particular section. And this one is a constant. The OXO and the DXD divided by the V sub S plus 1. So this is your slope and this is your y-intercept. For a MCCABE-THIELE plot for, shall I say, distillation with side stream removal, your operating lines will be adding depending on the number of side streams. In this case, class, you have an additional line here for your side stream, for that stream which was withdrawn. This is your enriching section operating line. This is for the side stream. This is for the feed stream. And this is for the stripping section operating line. Now, when we speak of the partial condenser, we are actually using two types of condenser in our column. These are already talking about the auxiliary equipments that we will be needing in our column. And actually, there are problems in the board exam which talks about distilling columns with condensers and even parameters related to the condenser. So, it's important that you understand the two types of condensers that are being used. So, we have the partial condenser here. And it's equivalent to this particular first stage when you are drawing your graphical approach to determining the number of stages for your distilling column. So what about this partial condenser? So it's used in cases where the this is used in cases where the overhead distillate product is removed as vapor instead of liquid. So you want to remove a product that is not fully converted into liquid. So then you have to use a partial condenser. This is used when the low boiling point of the distillate makes complete condensation of the same possible. Now, if there's a very low boiling point for your vapor that goes up, then full condensation or complete condensation would be difficult. And as such, a portion of your vapor will remain unconverted to liquid, and it is withdrawn as vapor in that case because it's impossible to have a 100% conversion. The liquid condensate is returned into the column as reflux naturally because it was already converted into liquid. The portion that was not converted into liquid is removed as vapor. So that's in the case of partial condenser. When time of contact between the vapor product and the liquid is sufficient, the partial condenser is considered another theoretical stage. So when we draw the column, our condenser now will be considered as another theoretical stage. That is a partial condenser. What about a total condenser? So the total condenser is the most often time used auxiliary equipment because it converts everything, the vapor that goes up, into liquid. It condenses all the vapor and supplies both the product distillate, which is liquid, and the reflux also, which is liquid. Now, the concentration of the vapor from the top plate, the reflux, and the product in this case are the same. And we know that already, and this is often the case that is happening in the industry. When you speak of efficiencies for distilling column, it has something to do actually with the time of contact and the degree of mixing of our phases, the liquid and the vapor phases in a tray or stage. Now, if it is insufficient, the stream, referring to the liquid and the vapor, leaving the stage will not be equilibrated, or it will violate equilibrium because they were not there was no assurance that they were completely mixed and their time of contact is enough for the recovery, for the desired recovery. So in this case, our tray will not be functioning 100% efficiently. So the efficiency is less than 100. Now, if stage efficiency is less than 100%, the number of actual stages to be used to achieve desired separation will be a lot more than the computed theoretical. So if we have already determined the efficiency, what we have computed by design as the theoretical number of stages will not be the actual stages later on when we put up the column. Now, how do we determine the efficiency of our distilling column? So we have the crudest way of determining the efficiency, and that's the overall tray or plate efficiency, the E sub O. We simply take the ratio of the number of ideal trays to the actual trays that was used. The number of ideal trays is actually the theoretical number of trays computed, wherein the number of the actual trays, of course, the one that is followed in the design. Meaning we add something to the one that we have computed to compensate for the efficiency of our trays or plates. Now, this is least fundamental, is concerning the entire tower, and I have already defined to you the definition. So it's the least fundamental. So meaning of accuracy, it may not be as accurate as the other ways of expressing tray efficiencies. Then we have the Morphy tray efficiency. And the formula you could see there. Now, it will be using the y sub n, the y sub n plus 1, and the y sub n asterisk. We know it's the y sub n because it's the mole fraction of the vapor leaving tray n. That's our representation. The average actual concentration of the vapor leaving tray n. So the term there is average because you are actually taking all the concentrations of the vapors that leaves that particular tray and take the average of that. That's based on the tray n. The tray n plus 1 is the average actual concentration of the mixed vapor entering. So if y sub n is leaving, y sub n plus 1 is entering. The difference of the asterisk here, y sub n asterisk from the y sub n, is this time it is the concentration of the vapor in equilibrium with the liquid leaving the tray. downcomer, or leaving a specific tray through the downcomer. So everything in the formula on efficiency class that has the presence of the asterisk represents equilibrium condition. So and that's your more free tray efficiency. Now, it does not compute the efficiency of the entire tower, just like the overall tray efficiency, but it solves the efficiency based on a particular tray N. Tray N. So, more free tray efficiency. So, if you be asked which of the two will be more accurate, then we say it's the more free tray efficiency that will be more accurate, because it's now looking into efficiency of a specific stage or tray. What about the more free point efficiency, or the point or local tray efficiency? So in terms of subscript, you have the P already added to the M. Now you still have the Y's, just like the before the previous formula, but but this time it's prime. Why do you think it's a prime? Because this time, we're not taking the average concentration of all vapors leaving a particular tray, but rather, we're taking the concentration of a vapor on a particular tray on a specific point on the tray. On a specific point on that tray. So, concentration of the vapor leaving a specific point on tray N. So, this is even more accurate because you're not basing it on the tray, but you're basing it, I'm referring to efficiency, on a specific point on the tray. And that's your more free point efficiency. Again, your asterisk here represents equilibrium condition. Concentration of the vapor in equilibrium with the liquid living at the same point mentioned in here, or the same point wherein y sub n plus 1 and y sub n was based on. So it's now based on a point on a tray. So of the three, it's the more free point efficiency which is the most accurate. So in terms of representation, this is it. This is your y sub n. You take the average of the vapors here that goes up. Your y sub n prime is based on a specific point. This is the point. And your y sub n plus 1 is for the average of the vapors that's still about to enter tray N. Now, on trace efficiency, so let's have a look into principles of tray efficiencies. We have y sub n prime cannot be greater than y sub n asterisk. As such, local efficiencies cannot be more than 100%. The concentration of the vapor leaving a particular point on tray N cannot be still greater than the concentration of the vapor in equilibrium with the liquid leaving that particular tray. That's your y sub n asterisk. On small diameter towers, the vapor flow sufficiently agitates the liquid so that it is uniform on the tray, which makes the concentration of the liquid leaving the tray the same as that on the tray, making the point efficiency equal to the more free efficiency. This is in the case of small diameter towers. The discrepancy, or the difference between more free point efficiency and more free efficiency is very negligible. In large diameter tower, of course, we expect that since more free point efficiency is much more accurate than more free efficiency, then this one would be higher because this one is less conservative. That is in the case of large tower. As to relationship of the different efficiencies, so our overall tray efficiency can give us actually the more free efficiency based on, or that is if we know the slope of our equilibrium line or curve, and we know the ratio of the V to L, or that is the slope of the operating line, which is L over V. So M over L over V. Now, in terms of efficiency of random packed and structured packed towers, so now it points us to the concept of the height of the packed column necessary to give a separation equal to one theoretical plate, or that is the HETP. If we intend to determine the height of our distilling column, that would simply be equal to HETP times the theoretical number of stages. And this is exactly the way we do it in gas absorption or stripping, if we intend to use the HETP formula. Now we have the Hognog, and this was defined as well also before to you, and we determine the HETP. We can determine the HETP based on the Hog, or the overall height of a transfer unit, and you have everything here defined as well. The only time that these two will be equal is when your equilibrium line and your operating lines are said to be parallel. As for efficiencies and height of tray and pack towers, so take note, how efficient and how high is your tray and pack towers, there is this set of formulas available in Jan Couplis. You have this set of formulas available in Jan Couplis specifically for each particular type of service or tower. So please look into this. If it's not available in your handbook, kindly look for the equivalent. If an equivalent is not available, then you may write it in your handbook, because anyhow, it's just a formula. Now, when the graphical approach is used in determining the efficiency or the Moore free tray efficiency, the equilibrium curve is this. We draw a new equilibrium curve depending on the Moore free efficiency, because it's the oftentimes used or the most used method of determining efficiency. And we start off stepping off our number of stages until that curve only. We don't, because this is now your curve when the operation of the tower is not 100% efficient. Since the last stage is the reboiler step, we don't add it to the number of stages. So it's the same thing with the previous discussed procedure of determining the number of stages graphically. The last step is the reboiler, so you don't count for it when you determine the number of stages graphically. If you're using a partial condenser, you don't count for the first stage in here. But if it's a total condenser, you still count it because it's still part of your column. Okay. As for distilling columns, we have energy balances for the column, and we have this when this equation available. This is taken from MCCABE. This equation allows you to determine the condenser duty, or the amount of heat that is to be the amount of heat that is to be absorbed by the cooling water in the condenser, so that it will be able to condense the vapor or convert the vapor into liquid. The V sub n plus 1 is the vapor leaving the top plate of your column, and these are your other parameters in the equation. Your condenser duty is your V sub n plus 1 is the vapor that goes back to your column from the reboiler, or it's the vapor that goes up the column coming from the liquid that was converted into vapor by the reboiler. That's your V sub 1. The V sub n plus, that's your V sub n plus 1. Your V sub 1 is the vapor that leaves the top plate of your column. Again, I was mixed up there. Your V sub 1 is the vapor that leaves the top plate of your column. The V sub n plus 1 is the vapor that enters your column, the first vapor stream based on numbering that enters the column after part of your liquid that goes down was converted into vapor by the reboiler. So for you not to be confused, the V sub n plus 1 is the same really as in the representation for gas absorption, because V sub n plus 1 is the V at the bottom of the column and V1 is at the top of the column, the one that is withdrawn on top of the column. So it's the same thing here. So don't be mixed up. Now this is the operating line for your upper part of the column when you're doing energy balance on the upper portion, because your goal is you'd like to find the condenser duty. So your final working equation on the top of the column, Your final working equation rather for the entire column, not just the top of the column, will be this one. So this still assumes constant molar, this does not assume constant molar overflow. So this does not anymore assume constant molar overflow. And QC is said to be condenser duty. Take note, for a total condenser. So if the problem is a partial condenser, there must be something wrong with that, because we only account using this equation, and using this equation for condenser duty, all the streams in here if your condenser is a total condenser. If it's a partial condenser, then we cannot use the same equation anymore. You have to set up your own energy balance on the condenser. That way you can do the energy balance properly. Again, your constant molar overflow will not be anymore assumed in here. So it's not being assumed. This is for determining the condenser duty of your column. Now, for the reboiler duty, I like to go straight to the reboiler duty. It will be needing the condenser duty. So it makes the energy balance on the entire column already. This one comes from the energy balance on the lower portion of your column where your condenser is situated. So what you need only to take note here is the final equation for the condenser duty and the final equation for the reboiler duty. Okay, MCCABE has this equation also, and I think this is coming from him if I'm not mistaken. So if you cannot find this in MCCABE, then it also came from John Kuplis. If you have an equivalent of this in the handbook, so much the better. But if not, please make sure that you will be able to find an equivalent of this. Now, in terms of heating requirement, these are actually equations that you can use for problems in terms of steam requirement or steam consumption. Steam consumption where the reboiler uses steam to convert the liquid that goes down into vapor. And this is your formula for finding the steam consumption. The V bar is the vapor rate from the reboiler. The lambda S is the latent heat of steam, and the lambda is the molar latent heat of the mixture. The heating requirement, and that's your steam requirement. For the cooling requirement, of course, it's in the condenser. Your condenser needs cooling water to convert the vapor that goes up into liquid. So this is the formula. It will be needing the CPW, the temperature rise of the cooling water, and the specific heat of this one. The CPW class is, there's something wrong with my slide here. The C sub PW should be here. Naglumpat na siya. That's the specific heat of cooling water. The T sub 2 minus T is the temperature rise of the cooling water. There's no need for you to really observe the difference in terms of numerical, in terms of the signs. What you need here is just the numerical difference in the temperature. So final temperature minus initial temperature. So that's the rise in the temperature of the cooling water. This is for the specific heat of water, and that would be for the molar rate of cooling water. Again, this lambda is the same lambda that was mentioned here, which is the molar latent heat of your mixture. Okay? These two formulas is from, I'm sure this one is from MCCABE. So again, look for its equivalent in your handbook. And that's the end on the very long topic of distillation, comprehensively around, like probably around, let's say 60% comprehensive, because we haven't delved with the actual design of each of our types of columns for distillation, even though this is how long it is already. Okay, I will send a recording for the other topics once done already.